So this is a suspension bridge. This is question 30, right?
Yeah.
7B. So a suspension bridge is a bridge which has been suspended. That is why it's called a suspension bridge. So you have some kind of a deep foundation that is made over here. Okay, and you have poles. Sometimes if the bridge span is very long, you can also have poles in between. But basically what happens is then you suspend cables from that, and from that you suspend further cables, and then the platform of the bridge rests on that suspension. Okay, so technically what can happen is the bridge can sway back and forth, right?
Yeah.
Did you see the video of the bridge collapse? I had posted that in the classroom. Have you seen that?
Yeah. I saw that.
You saw that, right? Okay. So the same thing happens over here. Let's say that troops are marching up and down this. Okay. This is some kind of a goose stepping soldiers. All right. So what happens is if there are a lot of soldiers who are marching, the march is supposed to be something that is in unison, right? So there is a rhythm to it. Okay, they go left, right, left, right. Now what will happen is when everybody puts down their left foot, naturally the bridge is going to sway away, that is into the whiteboard as it were. And then when they bring down their right foot, the bridge is going to sway towards the camera, outside the whiteboard. Now, if they are going to march across the span of the bridge, more and more people are going to come on, more and more people are going to step once to the left, once to the right? So what will happen to the movement of the bridge, the oscillation of the bridge, the amplitude of the bridge's vibration?
Yeah. It'll increase, right?
It will increase, right? The amplitude will increase. The frequency will more or less remain the same, but the amplitude of the oscillation of the bridge will continue to increase. Okay. Now, what is that phenomena called? Resonance. Okay, so what is happening is the frequency at which the soldiers are marching left, right, and the frequency of the natural frequency of the bridge, if it kind of happens to be matched, then what will happen is the bridge will start oscillating violently, and that can actually lead to structural damage and collapse. So when soldiers are asked to march over a bridge, when they have to march across a suspension bridge, in particular a suspension bridge, then they are told to break step, which means that you are not supposed to march left and right. I don't know how exactly they do that, whether they tell the first row of people to march with left and then the next row to march with right, or they just tell them just walk across, you don't have to march. I'm not sure about that, but they are told to break step so that they reach the other side of the bridge safely. So that is the answer to this question.
Sir?
Yeah.
In the winter, does the bridge move so much because of the wind or what? Why is it?
Yeah, in that case, it was the wind that caused the resonance. The gusts of wind which were coming up the Narrows River, that caused the swaying to increase more and more. It just so happened, they did not plan for that in particular, that the frequency at which the gusts of wind were coming and the natural frequency of the bridge unfortunately got matched. And it went on for such a long period of time that from a small oscillation, it increased to such a large oscillation that the bridge itself eventually collapsed because it got structurally compromised. In fact, the same thing can also be used in earthquake-proof buildings. So when you have very large skyscrapers, then because in these skyscrapers, you have a very large surface area which is exposed, right? So if there are huge gusts of wind which are falling on the building, and it so happens that the building's frequency with which it, because it's a tall building, right? So there will be a frequency with which it vibrates. The structures have to vibrate to that. So then what will happen is the building can also start vibrating. This is an exaggerated vibration, but much like the times of a tuning fork, the building can also start vibrating and collapse. So they have to factor for this. In Japan, what they do, interestingly, because they have to make their buildings earthquake proof, right? So they do this in a very interesting way, and you can look up some videos of this also. What they do is, right on top of the building, they suspend a huge weight. Okay, so of course it is concealed in the case of buildings. Now, what does that do? How does that help? Suspending a large weight at the top of the building.
It actually stops it from shaking. This bob thing, this large weight thing, it's even used in very tall buildings like the Tepe 101.
Yeah, exactly. So that is what I'm saying. This is a tall building. So what they do is they put a huge mass at the top, which is freely suspended. So what will happen is when the building moves to one direction, say because of an earthquake or because of winds that are incident on it, the inertia of that mass remains in place. Okay, and because the inertia remains in place, when the building comes back, right, the inertia will then swing this direction. So that causes a damping effect to take place. So these are known as dampers. Of course, they have to take care. Ashok is saying what they hit the side walls. Of course, they have to take care that the oscillation of that large mass is not so great that it will damage its own structure. But it can be designed in such a way that it swings in such a way that it doesn't bang into the sides. And those dampers can prevent this kind of problem from occurring. Runaway resonance. The same thing is also done in another structure. You people must have seen high tension power lines, right? High tension power lines are these things. So you have these cables that are suspended across for power grids, right? So it can also happen, and just to give you a kind of an idea of the scale, that's the size of a human. Okay, so these cables that are hung across, right, can be up to 100 meters far from each other. So you are having a 100-meter aluminum cable which has been suspended, quite thick ones. Okay, they can be, you know, about the thickness of these two or even three pens put together, depending upon the voltage that it's carrying. So these are extremely heavy objects. Okay, so what can happen is, if the wind is blowing again, these cables can start oscillating to and fro, right? And if destructive, that is runaway resonance, starts taking place, then these structures can also oscillate so much that the entire pylon structure can collapse. These are called pylons. So what they do is they add dampers to these cables. So right at the ends over here, you observe carefully the next time you go. Okay, they add these structures. So if you show it in a larger scale, so you have the cable, right, and suspended from this cable, you will find an object, a metal object with masses suspended at the ends. Okay, and these objects are called dampers. So how does that damper help? These can, of course, oscillate like this. Any responses? Are you all still here? Yeah.
Yeah, I think it tilts when the wires move.
So what will happen is the dampers will rotate when the cable starts oscillating to and fro. The dampers will turn around like this, right? And the dampers are not going to be at the same frequency because the masses at the ends, they have inertia. So they will tend to remain in their place when it swings to the other direction. And then when it comes back, it will swing in the other direction. So because of this movement, what will happen is it will break the frequency. And when it breaks the frequency, it doesn't allow runaway resonance to happen, and thereby preventing a catastrophic collapse. So these are just some ways in which resonance is prevented in structures, and also therefore how resonance can be destructive. The basic argument about characteristics of sound is that we have studied sound as a kind of a physical phenomena. Okay, so all that we have studied so far in terms of its frequency, in terms of its wavelength, in terms of various phenomena that is associated with it, like forced vibration, resonance, and so on. These are measurable phenomena, but there is one other entire side to sound, which is subjective. Okay, like say for example, loudness of a sound is something that is subjective. How? Now you all must have, I mean, you're all teenagers and you all must have experienced this at home or elsewhere. You're playing your music, not in your mobile phone through the earphones or headphones, but you're playing it out on your speaker. There's some fun in it, right? You turn on the sound, you switch off all the lights and you're enjoying your music, whatever it is, right? And there's a knock on the door, and a parent or an older sibling says, why do you have to listen to the music so loudly? And you say, it's not loud, right? So something that may sound too loud for someone may not be loud for another person. So therefore we say it's a matter of subjective opinion. One person's loud sound may be another person's music, and you may say that, look, I'm listening to whatever it is that you're listening to. I'm listening to heavy metal, and heavy metal is meant to be heard in this way. You're meant to hear it loud. That's when you get the music. And they say, well, it's too loud for the house. You have to turn it down or use your headphones. But the loudness obviously refers to a specific physical phenomena, right? And that phenomena is something that is measurable. So in terms of sound, loudness is something that is akin to what is known as intensity of the sound. We call it intensity, sound intensity. And what is sound intensity? Any object that is vibrating, right, has to transfer energy to the air particles around it. Okay, so the air particles gain energy as a result of the vibrating object. Now the amount of energy that you are putting into it, right, in terms of joules per per unit surface area is called intensity. Okay, so let me repeat that. Energy per second per unit area, right? So something that puts more energy per second in the same unit area, right, will obviously produce a larger sound compared to something that puts less energy per second per unit area. Is this something that is understandable, or do I need to discuss this further? Okay, what about the others? If anybody has a doubt or a question or is not clear about this, then you have to ask.
So will this be related to amplitude?
Yes, of course, it is related to amplitude, because the more energy that you give to air particles per second, that energy is going to get converted into potential energy, right? Elastic potential, because the air particles have to compress. So the more that it goes from its mean position, further away it goes from its mean position, the louder the sound is going to be.
I have a question.
Yeah.
Then how is it subjective since the amplitude changes?
I'll come to that. So Isha is asking, well, if the amplitude is changing in terms of energy per second per unit area, why does it end up being subjective? This is a measurable thing. So the answer to that is, well, intensity is not subjective. This part is objective. So we are looking first at the objective quality, and then we will say that, okay, how does that tie up with the subjective quality? So you have a sound, I'm putting it in intensity. Oh no, it's not intensity. It's the displacement about the mean position. Okay, and this is in time. Right? And let's take a sound like that. So what is the difference between this sound S1 and this sound S2? Okay, the frequency seems to be the same because it's completing one oscillation in that time frame, in the same time frame. The wavelengths also seem to be the same, right? So what is different will be the displacement about the mean position. So why is it that the particles are moving more further away from the mean position in this case in comparison to this case? Well, it has to be because of the energy that is provided to it. The object which is causing this is vibrating more about its mean position than this, right? And that is the difference between striking a tuning fork lightly So I strike the tuning fork lightly and I strike it hard. So the difference is that the times of the tuning fork are going to be displaced more when I hit it hard than I hit it slowly. Okay? So the amount of energy that is given out in this case is more than in this case. So that is why the intensity is higher over here than in this case. Is that clear now? Rudra, specifically, which
So
part?
the intensity part, the right now.
Yeah, is that Rudra, by the way?
Yeah, sir.
So what I'm saying is that you can recognize from this graph that the frequency and the wavelength is the same for both S1 and S2. Okay, the difference that you see is that the displacement of the particles about the mean position is more in this than compared to this. Why would the displacement be more in this compared to this? Is because the nature of the object that is oscillating. I can speak very softly and I can say the same thing very loudly, right? So the difference between those two things, I didn't say the same thing very loudly, but what's it? I can say Rudra. I can say Rudra. I can say Rudra. The difference is that I am causing a greater change in the mean position. So therefore, I am spending more energy over here than over here. So that is what ties it up to the intensity. Is that better now, the understanding?
Yeah, sir. Yeah.
Okay. So now that we have got the idea of intensity clearly, we can ask the question, but really in terms of energy, how much is the intensity? Why don't we just talk in terms of loudness as intensity? Why do we have something different for loudness? Okay, so the problem is that the amount of energy that we measure in terms of joules for sounds is so small that a strange thing happens. Okay, so let us take some of the softest sounds that you can hear. Okay, barely audible sounds, something that the textbook connects to this idea. You know, they keep harassing students about pin drop silence. You have heard this? I need pin drop silence. What do they mean by that? Teachers kind of say this in terms of class control. What are they expecting when they ask for pin drop silence?
So that when they drop a pin, you can hear it.
Yeah, so I want everybody to be so silent that you drop a pin in the class and I should be able to hear it. So we say that pin drop sound is one of the least audible sounds that can be produced. Let us assume it like that. It is like that, okay? What is the amount of energy in terms of intensity, how much it is? Pin drop silence kind of relates to a sound which is 1 in, 1 followed by 12 zeros. 6, 7, 8, 9, 10, 11, 12 joules per second per meter square. Okay, is that a lot of energy or is that a very small amount of energy? It's an extremely small amount of energy. So that is the typical range of kinetic energy that these particles gain when you produce a sound which is somewhat like pin drop sound. It's not pin drop silence, it is pin drop sound. Okay, and that can of course be written, your class 10 students, so you should be able to write it in terms of exponents. 10 to the power of minus 12 joules per second per square meter. Okay, and that is also for a square meter. It's like this amount of energy is invested in an entire square meter. Why is that? It's because when a pin falls to the ground, and it hits the surface, right, it produces a bubble of sound around it, right, which then radiates outwards. Of course, I'll have to show it as a full bubble. Okay, and that bubble of sound, if it were to be increased to 1 square meter, the surface of it, right, then the energy that is contained in it will be 10 power minus 12 joules per second. Is this kind of making sense?
Yep.
Joules per second, of course, has to be written in, can be written as watts, right? An amount, the power produced by an object which is converting energy at the rate of 1 joule per second can be called as 1 watt. Have we done this already? In energy, we have done it, right? And we studied in class 8.
Yeah.
Yeah? Okay.
Power and
Kind of vaguely remember. Please look it up. If you have your conceptual physics, you should look it up. Okay. So therefore, now we can kind of build a chart of how much energy is put in. So the least audible sound that you can get is something like a pin drop, leaves rustling, it says in conceptual physics. And that energy is something like about 10 to the minus 12 watts per square meter. Okay. Then the next more audible sound. Somebody's in the waiting room. Nobody. Okay, something like a whisper, like you softly whispering to somebody, let's say in the class, right? The amount of energy that is typically there in this is 10 power minus 10 watts per square meter. Right? And then conversation, like a group of people, 4 or 5 people are kind of talking to one another. It goes to something like 10 power 6 minus 6 watts per square meter. A busy street, something like 10 power minus 5 watts per square meter. Going up to a loud disco. And by disco I mean a discotheque. How many of you have been to a discotheque? Have you been to a discotheque? I'm asking because have you experienced the sound?
Yes.
Yeah. Like these DJ parties that happen in Maharashtrian weddings. That kind of loudness. I don't know how those people can stand in front of those speakers and dance.
Now I know why.
I think I'll faint if I had to do that.
They turn out to be half deaf later on in life.
Yeah, you can't hear things properly for a few seconds, even if you just like kind of pass by that area. I don't know how those people.
These are also the people who live in houses screaming in every conversation. Like you can hear it in the next house. It's that loud.
You not go deaf after such weddings.
And actually, if you go there, I can feel the vibration so much.
Yeah, you can feel it in your body.
Yeah.
That happens.
So your feet are vibrating after a little while. Okay, so these are some really loud sounds. Okay,
so
and you can kind of like go all the way to I'll just hear you, and let me just put this in a jet engine. Sometimes you can hear the jet engine in some smaller airports, right? Like you get off the plane and the engine is still running, but a jet engine which is like 30 meters away, running at idle speed, can produce something like 10 to the power of 2 watts per square meter. 10 to the power of 2 watts per square meter is just 100 watts per square meter. Okay, yeah, now somebody wanted to say something.
Yeah, so almost like what you were saying, like the jet engine, there's that
slowly,
part of the.
Please, I'm not able to catch you.
Yeah, there's a part of the aircraft, right? I don't know the name of the part, but then I think it's called the jet engine only. So like some people they stand close to it while entering the plane, right? So that's also like 10 to the power 2 watts per meter square, right?
It could be pretty loud. Like say for example, I don't think they will expose passengers generally to this kind of a volume of sound, because this jet engine at idle speed in 30 meters is not something, it's actually painful sound.
Like we need to pass it, right? We need to pass it to get to the other side of the plane.
Yeah,
like outside the plane.
So
I think that's more dangerous than the discos, right?
Dangerous than the discos.
Disco.
Yeah, but disco, the problem is that you are going to have prolonged exposure to the sound. Whereas jet engines, it's going to be only for a short while. But yes, this kind of volume is very high. And who is exposed to that? Not passengers, but the crew, the ground staff, the ground crew. So if you see people who direct the planes and so on, the guys with those semaphores in their hand, those people have to wear ear defenders. They have to wear noise cancellation, sound cancellation devices, which will cut out the sound by actually producing counter sounds. We will come to that. Destructive interference is used in that. Okay, so normally speaking, jet engines, they will not allow you onto the tarmac, or they will not turn on the jet engines at high speed when passengers are there in the tarmac. So at idling speed, it will go to the runway and then they will start increasing. But even if you're sitting in the plane, you can make out that the engine sound is becoming pretty high, the loud whine. Okay, so let us move on now. So the thing is, sound intensity, while it is measured in terms of watts per square meter, right, is not a good way, because this is a difficult progression to handle. We are talking about very low amounts of energy. So what they came up with is they equated this sound, something like about 10 power minus 12 watts per square meter. They gave it a new unit of 1 decibel. Okay, where dB stands for decibel, and the bell, of course, is named in honor of Graham Bell. Although Graham Bell is with 2 L's, this is with only 1 L. I don't know why they did that. But the sound of 10 power minus 12 watts per square meter, they equated to, I beg your pardon, not 1 dB, 0 dB. Okay. Then 10 power minus 10 was equated to 20 decibels. So 10 power minus 11 will be 10 decibels. 10 power minus 6 will therefore be.
So what?
60.
So they made it linear, right?
No, they made it logarithmic.
Yeah, but but it's linear now, right? 20, 30, 40. No, wait.
The power directly translates to every 10 decibel jump.
Okay.
Okay. And then what have I written? 10 power minus 5 is 70. Let me draw the line like this so it's clear. 10 power minus 1 will be therefore, well, 110 to 115 decibel, and 10 power 2 will be 140 decibels. And somewhere between these two, 70 to 100 decibel is the threshold of pain.
After you start breathing.
At the threshold of pain, which is approximately about 80 decibels, we are talking in terms of temporary hearing loss, some pain in the ears. Sounds above the threshold of pain can create permanent hearing loss. Okay? So your exposure to those loud sounds should be for a shorter period of time. Now, how we can arrive at these at the decibels from intensity, that we will discuss in the next class. There is a log relationship between these two things, which is not strictly speaking part of your syllabus, but we can discuss that also. We will see that in the following class.